Hello and welcome. So after 3 years hiatus, I'm staging a comeback, and today's lecture is about convolution. Now, convolution is, well, to put it in a nutshell, it is the process through which an input signal X interacts with the impulse response of a system, H, to produce the output Y. But what is even the impulse response H? You may well ask. Well, I'm expanding on this upon the completion of this lecture, but it is sufficient to say at this point that the impulse response of a system H, it is just a way of characterizing a system. Now, if you have a system, a mechanical system, or probably an electrical system, or even a biological system for that matter, and you would like to characterize it, and when I say characterizing it, I mean finding a mathematical way of describing its behavior. You would probably resort to differential equations. Now, the impulse response is just another way of doing so. So by evaluating it, you've successfully described this system. So without further ado, let's dig into convolution. Now, for sake of argument, assume we have a system with the following impulse response. So this is the system which is characterized by H, and this is H. Okay, this is H of n, and this is n-axis. Now H of n is simply 1, then 2, then 1.5. So this is 1, this is 2, this is 1.5. So this is the impulse response of a system H, and this is the input X, and this is the output Y. What this actually means is that if you applied an impulse at the input, so if the input was like this, impulse with the height of 1, then the output of the system Y is going to be like this. 1, then 2, then 1.5. So this is what impulse response means. Impulse response. So this is the response of the system H in case the input was an impulse. Okay, in other words, this means that if the input X of n was delta of n, then the output Y of n is equal to H of n. And I can even plot the two X and Y, the two signals, one under the other so that you have a better grasp of the timing here. So this is the output Y and this is the input X of n. Okay? So, and this is the impulse at the input. So at the very same moment that the impulse entered the system will output 1. And then a moment later it will output 2. And then a moment later it will output 1.5. Now I'm assuming here that the system H is actually an LTI system, that is linear time invariant system. And I'm touching on what these two properties mean one by one. Firstly, we have linearity. Now linearity implies that the system H exhibits the following behavior. If the input of the system was delta of n, and the output was 1, 2, 1.5, then what is going to happen if the input was 2 delta of n? So it's an impulse, but with the height of 2 instead of 1. So what is going to be the output of the system? Well, since the system is linear, then the output is going to be as follows. So instead of having 1, 2, 1.5, we're going to have 2, 4, and then 1.5 times 2 is 3. So, in other words, the output Y of n is equal to 2H of n. For such a system that exhibits such behavior, we call it a linear system. Now, next we have the time invariance. Now the time invariance, it involves that the system exhibits the following behavior. If the input up to the system was an impulse delayed by 1 second, so this is 0 and this is 1. So in other words, x of n is delta of n minus 1. Then if the system is time invariant, the output of the system is going to be, well, guess what? It's the same output but delayed by 1 second. So the output is going to be something like this. 0 and then 1, 2, 1.5. 1, 2, 1.5. This is 1, this is 0, 1, 2, 3. So we can write that y of n equals to h of n minus 1. Now, you can look at it this way. This system h has no sense of time whatsoever. So from the system's point of view, this is just an impulse. Regardless of the fact when it was applied to the input. So whether it was applied at n equal 1 or n equal plus 10 or minus a million, the system will just produce this output whenever the impulse arrives. So the system's only function is to produce this output whenever this impulse arrives. So if it arrives at n equal 10, produce this output starting from n equal 10. So this impulse will be produced at n equal 10, and this one at n equal 11, and this at n equal 12, and so on. Now let's have a look at another example showing the two properties of the system at the same time. So if x of n is, let's say, 3 delta of n minus 2, that is 0 at 0, and then 0 at 1, and then at n equal 2, the impulse arrives and it has a height of 3. So this is x of n and this is n-axis. Now we can intuitively find out that the output of the system is going to be 3 times h of n minus 2. That is 0 at 0, and then 0 at 1, and then at n equal 2, the impulse arrives and it has a height of 3, prompting the system to produce the output that is 3 times edge. Now edge, as you can remember, it was 1, 2, 1.5. So 3 times this is, 3 times 1 is a 3. So we have 3. And then we have the next moment, we have 2 times 3 is 6. So this is 6. And then 3 times 1.5 is, I don't know, 4.5. Okay, so we have 4.5, and this is 3, and this is 6. So this is the output y of n, if this was the input. Now, what if x of n consisted of 2 impulses? That is, x of n, we have an impulse with the height of 1 at n equals 0, and then another impulse at n equal 10 with the same height of 1. Okay, what is going to be the output of the system? Well, it is simple. So this is y, the output of the system. So with this, when this impulse arrives, the system produces the normal output, which is 1, and then 2 the next moment, and then the next moment 1.5. So this is 0, 1, 2. And then the system returns to the steady state, which is 0, 0, 0, 0, until the next impulse arrives at n equal 10. Then the system is prompted to produce the same usual output, which is 1, and then 2, and then 1.5. In other words, we can say that y of n is h of n plus h of n minus 10. So this is h of n minus 10, and this is h of n. Okay, now let's move on to the $1 million question. what is the output of the system going to be if those two impulses were actually adjacent? So, namely, if x of n was something like delta of n plus 2 delta of n minus 1. You see, the previous example was pretty easy because those two impulses were separated by 10 seconds. This allows the system to finish its response and return to 0 before the next impulse arrives. So when the first impulse arrived and excited the system, prompting it to produce this output 1 to 1.5. Now at n equal 2, the response of the system to this impulse ended and the system returned to 0, 0, 0, 0 until the next impulse arrived at n equal 10, prompting it to produce this output. If those two impulses were actually adjacent, the system won't have enough time to finish its response to this impulse before the next one arrives. So let's just break up the problem. When this impulse arrives, this will prompt the system to produce 1, 2, 1.5. Now this is not the final output, bear with me. This is just the response of the system to this impulse. Now, this impulse would be produced at the output, and then when n equal 1, the system was about to produce 2. However, there's a surprise. A new impulse arrived. A new impulse, which is this. Let's just call it delta of n plus 2 delta of n minus 1. So the new impulse arrived. Now, as a response to this new impulse, the system's supposed to produce something like this. 0, and then the impulse arrived at n equal 1, prompting it to produce 2, and then 4, and then what? And then 3. Okay, so it's just 2 times this. Now, what is going to happen is that the second impulse of the system's response to the first impulse at the input is going to be added with the first impulse of the system's response to the second impulse. So the final output is going to be something like this. 1 plus 0 is 1. And then 2 plus 2 is actually 4. So at n equal 1, the output of the system is actually 4. So it's not 2, not this 2, it's 4. The combination of the two. And then at n equal 2, the third impulse of the system's response to the first impulse at the input is going to be added with the second impulse of the system's response to the second impulse at the input. And the output is going to be 1.5 plus 4, and the result is what? 1.5 plus 4 is 5.5. And then we have 3 plus 0 is 3. Okay, so that's the output, 1, 4, 5.5, and then 3. Now to summarize, we can say that this was actually the response of the system to this impulse individually, and this was actually the response of the system to this impulse individually. This is edge of n, and this is 2, I guess, yes, 2 edge of n minus 1. And this is the output, y, which equals to edge of n plus 2 edge of n minus 1. So as you can see, the output of the system for the input x, which was actually delta of n plus 2 delta of n minus 1, was basically just a couple of impulse responses. This is just an impulse response. This is another impulse response, but it's multiplied by 2 and shifted by 1. and so on. If there was another impulse here and then another one, the output of the system is just going to be more impulse response, more edge of ends. But each one of those is being multiplied by a different factor and has a different shift, depends on the impulse at the input. So we can say in general that y of n, the output of the system for any input x of n, it is basically just a summation of edge of n. But each one of these impulse responses has a shift k, and k is just the index of the impulse at the input. And this edge of n is also multiplied by a factor that depends on the magnitude of the impulse at the input. So it's basically some summation of edge of n, but each one of them is having an amplitude that depends on the magnitude of the impulse, and a shift that depends on the corresponding shift of that impulse. So in general, we call this process convolution. So this is just x of n convolved with edge of n. This is the process through which the input signal interacts with the impulse response of a system in order to produce the output. And this is the philosophy of that stands behind the impulse response. If you get to know the impulse response of a system for a single impulse at the input, you will be able to find out the response of the system for any other signal in the universe, because all other signals are just basically a summation of impulses. Hence, the output of the system will just be a summation of impulse responses. In terms of analog signals, we say y of t is integration from minus infinity to plus infinity, x of tau, edge of t minus tau d tau. Now, before I wrap up this lecture, I want to show you something interesting. Remember what we did in the example? We actually convolved the signal 1, 2, that is x of n, 1, 2. We convolved it with edge of n, that was, let me see, 1, 2, 1.5. And the result was 1, 4, 5.5, and 3. So to recap, we convolved 1, 2. We convolved it with 1, 2, 1.5. And the result was, let me see that again. 1, 4, 5.5, 3. 1, 4, 5.5, and then 3. Okay, so that's the result of convolution. Something interesting is that if we multiplied 1 plus 2x, that is an algebraic quantity, we multiplied this polynomial by 1 plus 2x plus 1.5x squared. As you can see, these polynomials carry the coefficients 1, 2, 1, 2, 1.5. Okay, so let me start distributing the terms. So 1 is going to be 1 plus 2x plus 1.5x squared. And then we start distributing 2x. That is going to be plus 2x plus 4x squared plus 3x power 3. And then we start adding the terms with the similar exponent, that is 2x with 2x, and then 1.5x squared with 4x squared, and the result is going to be 1 plus 4x plus 5.5x squared plus 3x power 3. And voila, this is the same as 1, 4, 5.53, 1, 4, 5.53. Now, what the heck is going on here? I mean, how come the multiplication of two polynomials gives another polynomial with the coefficients as the output of convolving those two signals? Now, I'm pretty sure that you still remember the way that we got to the final result, 145.53. The way we got to this result is by, adding various versions of edge of n. So edge of n plus 2 times edge of n minus 1, and adding those together to arrive at the final conclusion. And this edge of n was actually the response of the system to this impulse. And then this 2 times edge of n minus 1 was the response of the system to this impulse. Now, edge of n was actually 1, and then 1.5, 2, and then 1.5. And 2 edge of n minus 1, when you multiply it by 2, it's like 2, and then 4, and then 3. All right. But as you can remember, through the addition of adding those two signals together, you have to pay attention to the timing of those impulses. So we had to add the second impulse of the system's response to the first impulse at the input with the first impulse of the system's response to the second impulse in order to get the second impulse of the response output of the output response. And so it's a pretty cumbersome and inconvenient operation because you have to pay attention to the not only to the magnitudes of the impulses, but to the timing of these impulses as well. So you can't simply just add 1 plus 2. You can't do that because this impulse takes place at a different time instance from this. So as you can remember, we have to add this 2 with this 2. So it's like this one with this one, and then this one was added with 0, and then this one with this one, and then this one wasn't added with anything at all. So you have to pay attention not only to the magnitudes, but to the timing as well. So we have to draw two axes for the amplitude, another axis for the timing. So is there a more simple way of doing this? Now, as it turned out, yes, there is. By utilizing algebra. You know, in algebra, you can't add 1 plus x. 1 plus x, this is just a irreducibly simple algebraic expression. You just can't add them because the exponent is different, just like adding 2x squared plus 3x power 3. You can't add this with this because the exponent is different. Now, we can take advantage of this property in algebra. You remember, we couldn't add this sample with this sample because they took place at different time instances. So what we're going to do is to encode x of n and edge of n to algebraic expressions, just like this. So the first signal, x of n, it was actually delta of n with a height of 1, and then another delta with a height of 2 at n equal 1. So this was x of n. Now I'm going to encode it to algebraic expression. Okay, this impulse, I will have the coefficient, the magnitude of the impulse as a coefficient, and then the timing of the impulse as the exponent of x. So it's x to the power 0. And then I'll put plus, and then I have the coefficient of the second impulse, which is 2, multiplied by x to power what? To the power of the time instance at which that impulse took place. So in this case, it's 1. So this x of n, which is delta of n plus 2 delta of n minus 1, was encoded to 1 plus 2x. Now the powers of x in these algebraic equations, algebraic quantities or just polynomials, represent the time instance at which each impulse took place, and the coefficients represents the height of these impulses. Now similarly, for the other signal, which is edge of n, Now edge of n was actually 1 to 1.5 to 1.5, 1. Now the algebraic transformation is 1 x to the power 0 plus 2 x to the power 1 plus 1.5 times x to the power 2. So as you can see, 0, 1, 2. That emanated from this 0, 1, 2. And then we have the coefficients 1, 2, 1.5, 1, 2, 1.5. Now these different exponents are going to make sure that those impulses will never be added together. So 2 will never be added with 1.5 because it took place at a different time instance. Now when we multiply those two polynomials, this one and this one, this is just call it capital X and this is capital H. When we multiply those two, we did this earlier, and as it turned out, when we start distributing, so 1 when distributed so it's being multiplied by 1, 2x and 1.5x squared is going to produce this. And then when 2x is multiplied by this, is going to produce this. So we just have two quantities, and this is equivalent to saying that this impulse will prompt the system to produce this output, and this impulse will prompt the system to produce this output. Okay, and that the final output is the summation of those two outputs. Okay, and the beautiful thing is that when you start adding those two quantities, those two polynomials, the addition process is going to be straightforward because you only going to be able to add the impulses that took place at the same time instance. So this impulse took place at n equal 1. It's going to be added with this impulse that took place at n equal 1. And this impulse, which took place at n equal 2, with this impulse, which took place at n equal 2. So we don't have to draw two axes and then we pay careful attention to the synchronization process and all of that. Okay, this concludes the video. The trick that I just showed you revolves around the Z transform, and I'm going to make a full video about that probably later. But for the moment, I just wanted to show you a glimpse into it. To wrap up, in this video, we explained how to convolve an impulse response of a system with the input of a system in order to produce the output. In the next video, I'll probably talk about an equivalent process to this one, which is multiplication in the frequency domain, and how to interpret this, how to interpret the impulse response in the frequency domain, and how to interpret the transfer function. So stay tuned in, and don't forget to hit the like button and subscribe. There's also a link to Patreon on my channel. A donation would be appreciated. It will encourage me to do more videos. And thanks for watching.